Hello everyone. Our question for today is the following integral. Integral from 0 to pi over 2, the ln of 3 sine of x dx. And this is called the Euler's log-sine integral. A similar integral was introduced by Leonhard Euler in the year 1769. So the integral that Euler solved that year was the ln of 1 times sine x. Alright, how do we approach this question? First of all, I'm going to apply the following change of variable. U is equal to pi over 2 minus x. This is du, and of course we have to change the boundaries because the current boundaries, which are 0 and pi over 2, correspond to x. But when we do a change of variable, of course the boundaries for u will be different. So if x is equal to 0, we get u equal to pi over 2. And if x is equal to pi over 2, then u is equal to 0. We come back to our integral, which I'm going to call I, and it now looks like this. Now here I want to interchange the boundaries, but of course I have to multiply by minus after that. One more thing I want to do here is I'm going to replace sine of pi over 2 minus u with cosine of u. And this is how I looks like now. Of course, we can replace the u by x or t or any other letter. This is called the dummy variable. So now I is equal to this integral as well as this. Let us add both expressions. So we get 2i on the left side and the sum of these two integrals on the right side, which of course leads to this. I will now put the sum under the same integral and use the following property: ln of a plus ln of b is equal to the ln of a times b, which gives us the following. We now use the following property: sine of 2x is equal to 2 times sine of x times cosine of x, which means sine of x times cosine of x is half times sine of 2x. And this is how I looks like now. I will reuse the property of ln. So ln of a times b times c is the ln of a plus the ln of b plus the ln of c, where a is 3, b is half, and c is the rest. And we get two simple integrals. So the integral of ln of 3 dx is ln of 3x from 0 to pi over 2. Same thing for ln of half. This expression is for the first integral. This is for the second. What about the third integral? I'll keep it like this for the moment. So our remaining task is to look at this integral. I will apply the following change of variable: t is equal to 2x, which means that our integral transforms into this, and this is how I looks like now. What we notice here is that this integral is very similar to I, but pi over 2 is replaced by pi. However, we will see that this integral is twice the integral from 0 to pi over 2 because x equals to pi over 2 is an axis of symmetry of the function f of x equal to sine x over 0 pi, as I will show you now. So let us consider the function f of x equal to sine of x over 0 pi. We have f of pi over 2 minus x is equal to cosine of x as well as f of pi over 2 plus x. This means that x equal to pi over 2 is an axis of symmetry over the interval 0 pi. Where did I get this from? Well, there is a theorem in pre-calculus which says that if f of a minus x is equal to f of a plus x over some interval I, this means x is equal to a is an axis of symmetry of f of x over I. How would this help us? Well, the integral that we have from 0 to pi can be now written as 2 times the integral from 0 to pi over 2. And the integral I pops up again, which means that this expression we stopped at can be expressed like this now. These twos cancel out, and this becomes 1/2 I. So the integral question is now transformed into a very simple equation. We're just solving for I now. I will take pi over 4 as a common and use ln of a minus ln of b is equal to ln of a over b. And this is what we get for the integral I. And actually we did not only solve the integral of ln 3 sine x from 0 to pi over 2. We have also solved this integral, ln of 3 cosine of x dx from 0 to pi over 2, because we proved that they are equal. And we get this result. We can even generalize this result by replacing 3 with a being greater or equal to 1, and this is what we get. Thank you for watching, and see you in the next video.